A research vessel is floating off the coast of California. It's 2024. A crew from Northwestern University just pulled a lump of rock the size of a potato out of the Pacific, 4,000 meters down. They hook it up to a voltmeter. It reads nearly 1 volt, a rock, sitting in the total darkness at the bottom of the ocean, generating electricity. Nobody on that boat expected that. And what they'd find over the next few months would force scientists to rewrite one of the oldest rules in biology. The rule that says oxygen only comes from life. Stick around because this isn't just a story about rocks. It's about why NASA has spent the last decade quietly building submarines for outer space, and why the strangest place in the solar system might be 4 miles beneath your feet. The place. America couldn't reach for most of human history. The deep sea floor was more remote than the moon. Not because it was far away. It's 13,000 feet straight down in places, but because of what's waiting there. At full ocean depth, water pressure climbs past 8 tons per square inch. That's the weight of a fully loaded pickup truck balanced on your thumbnail. It doesn't damage machines. It erases them. It took an American vessel to finally get a good look. In 1977, a 3-person submersible called Alvin, operated out of Woods Hole, Massachusetts, dove into the Galapagos Rift expecting to find a barren undersea desert. Geologists were only there to study cracks in the crust. Instead, their cameras caught something that made 0 sense. Gardens. Actual clustered colonies of foot-long tube worms, blind crabs, and dinner plate clams thriving around vents of scalding mineral-rich water, in a place with no sunlight at all. Up to that point, every biology textbook on Earth said the same thing. All life runs on sunlight. Plants capture it, animals eat plants, and the chain goes back to the sun every single time. Alvin broke that chain in one afternoon. Life that doesn't need the sun. What the Woods Hole team had found is now called chemosynthesis. Instead of harvesting light, microbes near these vents harvest chemistry, pulling energy directly out of hydrogen sulfide, the same gas that makes rotten eggs smell the way they do. Everything else in that ecosystem, the worms, the crabs, the eyeless shrimp, eats those microbes or eats something that ate them. It's a complete food web with the sun deleted from the equation. And once American scientists knew to look for chemosynthesis, they started finding it everywhere. Cold, seeping patches of methane on the Gulf of Mexico floor, crawling with tube worms that may live for centuries. Underground aquifers more than a mile beneath South African gold mines, where microbes have been sealed off from the surface for possibly millions of years, running entirely on energy released by radioactive decay in the surrounding rock. No sunlight, no surface contact, no problem. That last one is the detail that got NASA's attention. Why a space agency started building submarines. Here's the pivot most people miss. NASA doesn't care about Earth's ocean floor for its own sake. NASA cares about it because it's the best stand-in we have for places we can't send astronauts. Jupiter's moon Europa and Saturn's moon Enceladus are both locked under miles of ice, and both are hiding liquid water oceans underneath. Enceladus is so active it literally sprays that ocean into space through cracks near its south pole. The Cassini spacecraft flew straight through the plume and tasted salt, organic molecules, and hints of hydrothermal activity, all coming from inside a moon smaller than Earth's own moon. Which means the environment down there, crushing pressure, 0 light, rock in contact with water, is close to a match for the Gulf of Mexico seafloor or the bottom of the Mariana Trench. So NASA's Jet Propulsion Laboratory in Pasadena started treating Earth's oceans as a training ground. engineers built a slim, torpedo-shaped robot called Icefin and lowered it through boreholes drilled into Antarctic ice shelves, teaching it to navigate and hunt for life signatures in total isolation, the same way it eventually might under Europa's crust. A companion project, nicknamed Brewy, was designed to crawl upside down along the underside of sea ice, because on an ice-covered ocean world, the ceiling is where the action happens, not the floor. Meanwhile, off the coast of Florida, NASA has been sending astronauts to live underwater on purpose. The Aquarius habitat, sitting 60 feet down near Key Largo, hosts missions where crews train for the isolation, confinement, and hostile conditions of a Moon or Mars mission, because it turns out the ocean and deep space break the human mind in almost identical ways. The message from all of this is consistent. If you want to understand an alien ocean, first go understand this one. It's already here, it's already hostile, and it's already full of things that shouldn't survive. The oxygen that broke the rules. Which brings us back to that voltmeter reading. In the summer of 2024, a team led by marine ecologist Andrew Sweetman was running a routine experiment in the Clarion-Clipperton Zone, a nodule-covered stretch of Pacific seafloor between Hawaii and Mexico. They sealed off patches of the seabed in chambers and measured oxygen over time, expecting it to slowly drop as organisms consumed it. Standard procedure, done 1,000 times before. Instead, oxygen levels climbed. Not slightly. In some chambers, they more than tripled. The team assumed a broken sensor. They swapped instruments. Same result. They ran an old-school chemical titration test as a backup check. Same result. They even killed every microbe in the chamber with poison, on the theory that some unknown organism was somehow still producing it. Oxygen kept appearing anyway. That's when attention turned to the nodules themselves. Those potato-sized lumps of manganese, cobalt, nickel, and copper scattered across the seafloor by the trillions. Sweetman shipped a batch to chemist Franz Geiger's lab at Northwestern University in Illinois, and Geiger tested them the way you'd test a battery. Individual nodules produced up to nearly a volt. Clustered together, they produced enough current to start splitting seawater apart, pulling oxygen straight out of H2O through electrolysis. No biology required. If that holds up, it means oxygen can be generated by geology alone, in complete darkness, with nothing alive anywhere nearby, which quietly detonates a core assumption astrobiologists use when scanning other planets. The idea that finding oxygen in an atmosphere is a strong sign of life. Maybe not anymore. To be clear, this is still a live scientific argument. Other researchers have pushed back hard, questioning the equipment and the measurements, and as of this year, the debate is still playing out in the journals. Nobody has closed the case, but even the argument itself is a reminder of how little of this planet we've actually mapped. What's actually at stake? Here's where it gets uncomfortable. The Clarion-Clipperton Zone isn't just scientifically interesting, it's a target. Those same metal-rich nodules are packed with cobalt, nickel, and manganese, the exact materials used in electric vehicle batteries, and mining companies already hold claims to start vacuuming them off the sea floor at industrial scale. But researchers who went back to survey seabed that was experimentally mined back in the 1980s found something sobering. Decades later, life still hadn't returned to the disturbed tracks. Whatever function those nodules serve, oxygen production or otherwise, doesn't come back quickly once it's gone. So there's a real possibility playing out right now, in real time, off the American coast and beyond. An ecosystem nobody fully understands yet, sitting directly beneath a resource everybody wants. Put all of this together, and the shape of it is strange. A NASA-trained robot crawling the underside of Antarctic ice to rehearse for a moon of Saturn. Astronauts training for Mars, 60 feet under the Atlantic. A piece of rock in a Chicago area lab quietly generating a voltage nobody can fully explain. Every one of these threads points at the same idea. The boundary between ocean exploration and space exploration isn't as solid as it looks. The deep sea is where NASA goes to practice finding life somewhere else. And every year, Earth's own ocean floor keeps handing back results that look less like home and more like somewhere alien. So the actual question isn't just whether there's life on Europa, or Enceladus, or under the ice of some moon we haven't named a mission for yet. It's whether we've even finished exploring this planet first. If you want the next one, the story of what Cassini actually found when it flew through Enceladus's plume, let me know in the comments and subscribe so you don't miss it.